In this video, we're going to start our study of support vector machines. So support vector machines are this very famous machine learning model that probably many of you have used at some point, since they're such well-known models that work particularly well. But despite their popularity, their name is a little bit non-intuitive. So another way we can make things a little bit more transparent is to call them by a more natural way of thinking about these things and think of them as large margin linear classification. So this is just going to be, you can think of it as just a variant of the linear classifiers we've seen previously. But through some manipulation, we'll see how we can use the technology behind the linear form of this large margin linear classification and use it on models that support nonlinear decision boundaries. But for this video, we're going to focus on the linear case. So the outline is as follows. We're going to start by talking about what this idea of large margin is. What does it mean, and what is the reason for it? And one of the reasons is that it has a strong relationship with model complexity, right? Something we talked about previously. Then we'll talk about how to formalize large margins. So we're going to take the intuitive idea of wanting to have a large margin in our classifier, and figure out how to write that down mathematically as something that we can optimize, something that we can quantify and optimize. And that will lead to a quadratic program form of a large margin classification learning objective. And once we derive that, I'll show how we can relax that a little bit to allow for misclassification. So that will lead to a soft margin form of a large margin linear classifier. To start thinking about large margin, let's look at 2D data just so we can easily visualize. So suppose I gave you this data set that's pretty easy to classify, at least when we look at it with our human intuition, but there's positive data points in red and negative data points in blue, and you can imagine that our goal is to learn a linear separator that distinguishes one class from the other. So this is one possible classification decision boundary that separates the red pluses from the blue minuses. So this seems fine, and this is something that you might get out of the perceptron. But one of the strange things about this whole situation that I'm showing you here is that the dimensionality is small, right? It's two-dimensional, so you'd expect that it's really simple to classify this kind of data. And we have lots of examples, right? We have something on the order of, I don't know, 20 examples or so. And that seems like plenty to fill in a two-dimensional vector of parameters. But despite all that, there's actually a huge space of possible lines that can separate the blue and the red points, so that you get zero training error. So this line perfectly separates the points, so does this line, and so does this line. So when we have this kind of situation, the one question you might want to ask is, which line should we pick? Which of these lines is the best one, given what we know about statistics, the data distribution, and how our goal is not to overfit this data? So to help think about this, the question of which line do we pick, consider a different problem. So this is a different problem. So suppose we want to use something else to classify. We want to use a thicker line, a really thick line that separates one class from another. And in this picture, you can see that, well, you can probably imagine that there are still lots of different thick lines that separate these two classes of data. But this task, trying to fit a big thick line in between the two classes of data, is definitely a more constrained problem. And you can take this to the extreme, right? You can say, what if we have to fit a really, really thick line between the two classes of data? In fact, what is the thickest line we can fit in between the two classes of data? And we end up with something like that looks like this. And when we consider this form of the problem, we get something that doesn't have any opportunity for alternate versions of the predictor that might give you the same accuracy on training data. So if I try to wiggle this big, thick line in any direction, you can see that no matter what I do, if I move it in any way, we misclassify at least one of the points. So what we've done by this exercise of imagining that the line separating two classes has to be really, really thick is we've essentially imposed that the classification has to be done with some margin. There has to be some margin. You can think of it as a neutral zone that's neither one class nor the other. And then if you go back to the original idea of trying to find, what is the best line, based on this idea of getting a large margin, you could say that this is the best line, the line that splits right down the middle of a really thick region around the decision boundary that doesn't contain any points. And from a conceptual point of view, the idea of a classification boundary that has to have some margin is related to the idea of having a less complex model class. So if you are forced to separate your classes with a large margin, then you're less able to figuratively split hairs by barely separating two particular points in the data. Instead, we have to make very clear decisions about which points we think are positive and which points we think are negative. But that's a very loose view of the model complexity relationship with margin, and we'll look closer at that in a more rigorous way later. For now, let's say we believe the intuition that having a large margin will make you more robust to future deviations in sample randomness and any variance that we might get in the data sample that we were using as training. So if we believe that, then our goal should be, how do we computationally and mathematically find the large margin solution or the maximum margin solution? So let's try to think about how to write down the margin. So we'll start by introducing some notation for what we're talking about. So first we have a data set of examples with labels. So we have x1 and y1 through xn and yn, and each of the xi's comes from the real vector domain, so a real vector of length d, and each of the yi's in this case will be a binary classification label, and we'll use the -1 +1 encoding of a binary class. So the negative class is going to get -1, and the positive class is +1. So this is a convenient way to write things because then we can say that correct classification is characterized by this inequality, which says that yi times our weight vector dotted with the data example plus some bias term has to be greater than 0. And this is basically what we use for perceptron. And if we look at the requirement that it has to be greater than 0, what that tells us is that a point that's right on the line is sort of is okay with this constraint, with this requirement. So that's not ideal, because what we want is, we don't want the points to be right on the line. We want them to be as far away from the line as possible so that we have a good margin. So let's cross that out and write it again in a different way. So let's write now that the yi times the w dotted with x plus b has to be greater than 1. So it has to have a score, w transpose x plus b. That score has to be more positive than 1 if it's a positive label, or more negative than 1 or more negative than -1 if it's a negative label. And this has to hold for all data points from 1 to n. Okay, so this seems like we're on the right track, right? Now we've imposed that there must be some separation between the decision boundary and the actual score for each data point. But if you look at these two quantities, the w vector and the 1, you run across one problem, which is that you could always just arbitrarily scale w to be as big as you want. Multiply by some huge constant to the point where that this 1 is going to be negligible compared to the magnitude of w. So this doesn't get us all the way there yet. So what this does instead is it does impose that the data points, the data examples in our training data must be separated, must be correctly classified by some non-zero amount. So we have to do a little bit more to figure out how to find the W that gives us the maximum margin. So let's think more about what do we know about this margin? So if we look closer at these things, we know that on one side of the decision boundary, the prediction score is greater than 1, and on the other side, the prediction score has to be less than -1. And what we really care about is how much distance there is between those two regions in the original feature space, the space of X. So we can actually start to imagine points to reason about the distances. So let's imagine there's 2 points. There's one point on the plus side, a positive point. It's correctly classified to be in the positive space. And there's another point, x minus, in the minus space, in the negative space, that's correctly classified to be a negative example. And we could say that the margin is the distance between those 2 points. So here I've just written the formula for the distance in arbitrary dimensionality. And what I didn't write here is that the x and y points, ideally they should be the closest possible points to each other. So that means that you can just pick, without loss of generality, you pick one of them and put it on the decision, on the margin boundary. So that, let's say x minus is exactly equal to, or the score for x minus is exactly equal to -1, which is right on that cusp of where it's correctly classified with the margin. And then we say the same thing about x plus, but we also say that they're going to want to be directly across from each other, across the boundary from each other. And in order for them to be directly across the boundary from each other, the vector that separates the two, or the direction to get from one point x minus to x plus, is going to have to be at the same angle as w. So it's some scaling of w. So we'll call it gamma times w. And that gives us the equation that the vector x plus is equal to the vector x minus plus gamma times w. Or written another way, the x plus minus x minus equals gamma w. So now we have a bunch of equations that we have reason to be true, and we can do some manipulation of these equations now to try to figure out what we know about the margin. So let's isolate them. So the first thing we want to do is look at these equations and look to see if there's any ideas that we can combine together. So one idea is that we can see in this equation it uses x plus, but in this second equation right below it, it defines another way of writing x plus. So we should just, one thing we can do is just try plugging in the right-hand side of the second equation into the first equation. So we end up with this. We end up with, now we've replaced x plus with this other way of writing it, which is x minus plus gamma w. And now we have w transpose that plus b has to be equal to 1. So we can expand that a little bit by distributing the w into the terms in the parentheses. So we get now w transpose x minus plus b plus gamma times w transpose w, where I rearranged some terms just to move the w transpose x minus and the b together here, because that's actually something else we know something about, right? We know up here that w transpose x minus plus b has to be equal to -1. So we can plug that right in, and we get this new expression, -1 plus gamma w transpose w equals 1, which we can do some trivial manipulations, and we end up with the solution to what the value of this gamma scalar is. So we have gamma now, and we can take this and plug it right into yet another equation we've been we've scribbled on the screen, and we get that x plus minus x minus is equal to twice w divided by w dotted with itself. Okay, we're almost there, and this is exactly what we wanted, because this difference between the x plus vector and the x minus vector is pretty much the vector that determines the margin. We just need to measure the magnitude of that vector by multiplying it with itself and taking its square root. And we end up with this expression, which looks a little bit scary maybe, but things cancel very nicely, and we end up with 2 divided by the norm of w. So that's it. We now have derived from reasoning about two imaginary points that sit opposite each other on the margin boundaries, that the difference between, or that the distance between the two classification regions for positive and negative classes, or the margin, is exactly 2 over square root w transpose w. So if that's the case, then we can write down an expression that, or an objective that will give us the w that gives us the best margin, the largest margin. So we're going to maximize the margin, and we're going to constrain this maximization so that it has to give us a w such that all of the points are classified correctly according to this constraint down here. And of course, this objective function, we can solve it as in this form, but it's a little bit weird looking. What we can do instead, since all we're doing is trying to make this fraction bigger, we can do the same by making the denominator of the fraction smaller. We could just put that into a minimization, and we get this. And for the sake of taking derivatives easier, we can just multiply it by one half, because that doesn't make a difference, and we get the standard form of the linear large margin support vector machine. So this is good. And another reason that we wanted to sort of change the objective function form into minimizing this denominator here is that it now fits into a class of optimization problems that have been well studied and have algorithms for optimizing that have been really super optimized over the past few years. So the optimization algorithms have been optimized. And the class of problems is something called quadratic programs. And in quadratic programming, you have to take, you're searching for some vector x that minimizes some quadratic objective. So this is a form of a quadratic objectives where there's some H matrix and a F vector that determine the shape of this quadratic, subject to constraints that are linear. So you take some linear coefficients, multiply it by x, and it has to be less than or equal to some constant, and there can be many of them. So it's actually a matrix of linear inequality coefficients, and that there's also linear equality constraints. So a quadratic program has a quadratic objective, linear inequality constraints, and linear equality constraints. And a lot of times for different formal discussions, people often talk about quadratic programs as only having inequality constraints or only having equality constraints, but really it's the same thing, because you can do some tricks to convert between one representation and the other. So the more general form, and the form that's consistent with the software that comes with MATLAB, is that you can give it both inequality and equality constraints. So our large margin classifier fits exactly this form with a relatively simple definition for H and F. Well, F is just 0 in this case, and a also fairly reasonably simple definition for the linear inequality constraint matrix and constant vector. So that's it. This is the separable SVM, or support vector machine or large margin linear classifier. But I just gave it a little qualification there. I called it the separable case, and one of the things you'll see, right, if you just stare at the constraints, you'll see that we've required that the data points are all exactly classified, and that may not always be possible. So suppose we're given a data set, and we for either because of some noise in the data collection, or I don't know, that the features that we're measuring is missing some information that is critical to what causes one thing to be in one class or the other, or some other reason, we have some points that look to our human eyes like they're in the wrong place. And this happens a lot. This happens for lots of reasons in real data. And the problem with the form of linear classifier, or the objective function we wrote previously, is, no matter what you do, no line can properly or exactly separate all of the blue points from the red points. We just can't do it. There's no possible way to do it. So what we're going to do is we're going to just adjust the objective function so that it's still encouraged to try to correctly classify the points as much as possible. But instead, it will just be penalized when it misclassifies things, rather than it just being not a valid solution. Okay, so this is the original form, and you can see here are the constraints that are giving us problems. And just to complete the thought, if we had given this optimization problem with points that can't be separated to an optimizer, or to anybody, to some omniscient mathematical being that just takes in a math problem and gives you the answer, there is no answer. There's no W that will satisfy such a problem. So we don't want that. So what we'll do instead is we'll do something called slackening. And so we'll introduce some variables. So we'll introduce some variables psi. It'll actually be a vector of psi variables, one for each example, and we'll add a minus psi on the right side of this inequality. So these are the slack variables. So if you think about this, the psi variables essentially allow us to let the classifier cheat. So the classifier is trying to get the correct sign, is trying to beat the one, the margin of one requirement that we put it there. But if it can't beat it, then it can add some value to the slack variable and make the problem a little bit easier. And you can just make sure everything's going in the right direction. So the slack variables go from 0 to infinity. So if there's 0, if psi I is equal to 0, then it's like the original constraint, and you just need to make sure that it's actually classified correctly by at least 1. But if psi is really huge, if it goes towards infinity, then any possible W will satisfy this constraint. So of course we don't want the optimization to just choose arbitrary psi values, so we're going to add a penalty. So this term is going to penalize how big the slack variables are. And that C parameter, the C value, is going to trade off. It's going to say, how much does the optimization have to pay when it increases the slack? So if C is equal to infinity, then increasing the slack anything beyond 0 is going to cost infinite amounts. So that's more or less the equivalent of the original form of the problem. But if C is less than infinity, if C is which it always is, if C is a finite value, then you can think of the optimization as having to make a decision. Does it want to reduce the norm of W, which in turn increases the margin, or does it want to classify the points better? And it pays some amount for increasing the margin or for decreasing the margin, and it pays some amount for misclassifying points. So this is probably the most famous form of the support vector machine. So it's useful to just absorb what's on the screen. It's not too much, but try to make sure you understand what the slack variables do, how the classification constraints work, right? The way that it's multiplying by the sign of the label to make it so we don't have to write two separate constraints for when it's a positive class example or a negative class example, and try to understand that the regularization term, the W transpose W, exactly corresponds or directly correlates with the size of that margin. So what we're trying to do is find the maximum margin while making as few mistakes as possible, or not making as bad mistakes as possible. Okay, so to summarize what we talked about, so I first talked about large margin and model complexity, and I gave you some hints about how the requiring that we separate the data with a large margin, how that corresponds to a form of model complexity. Then we formalized how we can write down a mathematical expression for the margin of a linear classifier. Then that led us to a quadratic program that we can solve and get the solution to the large margin classification task. Then we talked about how we relax that to be able to handle situations where you have data that can't be exactly classified, or data that can be classified but not with the margin that you want, with the soft margin form. And we'll just finish up by talking about, what do we do once we have that quadratic program form? So what you can do, one thing you can do is you can use off-the-shelf quadratic programming solvers. So there's a bunch of these. There's one built into the MATLAB's optimization toolbox that's decently fast for small problems, or you can get some of these industrial strength solvers out there like Gurobi and Mosec and Cplex, many of which, if you're, well, for those of you who are students, you can get an academic license to use. And these methods, these software packages usually use interior point methods with barrier functions, right? Just like I talked about in the video about optimization. Some of them use other approaches, but most of them, for quadratic programs anyway, use interior point methods. And then another approach that people often take for solving this objective is to use gradient approaches. And there you replace the constraints with hinge loss functions. So that's where you get a penalty when you're wrong, and you get zero penalty when you're right. And that forms a funny looking loss function that's got a hinge, right? When you pass that margin constraint. And once you write things that way, you can take the gradient of that objective function and just take baby steps toward the optimum, just like we talked about in the optimization video. And then lastly, people will often use a dual form optimization. So this is a fairly new idea, at least in the context of this course, where you take the constraints from the objective function and replace them with penalty terms leading to saddle point optimization, just like the Lagrangian idea I showed you in the optimization video. And when you flip that around and do some manipulation, you end up with a totally different looking optimization that will give you the same solution, the same optimum, but has some very different properties. And furthermore, it leads to a very important discovery in the history of this method, and it will allow the mathematical ideas that we've derived here in the context of a linear classifier to extend to nonlinear classifiers in a very elegant way. So we'll get to that, and then we'll also talk about sequential minimal optimization, which is a fast way to optimize the dual form of the support vector machine objective.